Microsoft just dropped a bombshell that, if true, could redefine the very fabric of computing as we know it. Forget incremental updates. We're talking about a potential paradigm shift on par with the invention of the transistor itself. They're calling it the Myer One, and it's not your garden variety quantum chip. No. Microsoft claims they've conjured up an entirely new state of matter to make it happen. Let that sink in for a moment. We've got our solids, our liquids, our gases, our plasmas, and now, potentially, the new kid on the block. The topo computer, or topological superconductor. Is this genuine innovation, or just another bout of Microsoft's infamous overpromising? Is the multi-billion-dollar question. But if it's the former, if this isn't just smoke and mirrors, then we could be on the cusp of a technological leap that dwarfs anything we've seen in decades. Think about it. The humble transistor, that tiny switch, allowed us to scale computers from room-sized behemoths to the millions of bits humming inside your phone right now. Microsoft is suggesting that their topological computer could be the key to scaling quantum computers to millions of qubits without exaggeration. What does that even mean in practical terms? Well, if their claims hold water, we're talking about computers potentially billions of times faster than the current state-of-the-art. Imagine the possibilities. We could be on the verge of designing revolutionary new medicines at an unprecedented pace, simulating entire virtual worlds populated by incredibly intelligent AI entities. Maybe even those AI girlfriends the internet loves to talk about. And perhaps most miraculously of all, could we finally see Microsoft Windows updates complete in mere seconds instead of those soul-crushing hours we've all endured? One of the absolute worst experiences of my entire existence was the ill-fated upgrade from the stable, dependable Windows XP to the glitchy, resource-hogging abyss that was Windows Vista back in 2007. It wasn't just frustrating. It was a genuinely traumatizing experience that, in a strange twist of fate, actually pushed me towards the welcoming arms of Linux. So you can understand why, when I saw the headlines about Microsoft's audacious new quantum chip, a certain level of PTSD kicked in. Because let's be honest, as of today, quantum computers are, for all intents and purposes, utterly useless for the vast majority of practical applications. They're these incredibly complex, temperamental beasts that show flashes of brilliance in very specific, highly controlled environments. But they're nowhere near replacing your trusty laptop. However, and this is a huge however, the Myer One chip could represent a fundamental breakthrough. A potential turning point that propels us towards truly usable quantum computers, not in some distant, undefined future, but perhaps within the next few years. The stakes are incredibly high. According to Microsoft's enigmatic CEO, Satya Nadella, who probably delivers these groundbreaking announcements with the same calm demeanor he uses to discuss quarterly earnings. This unveiling comes just weeks after Google's own quantum announcement, their Willow chip. Now, Google, a major player in the quantum race, also admitted that their Willow chip, in its current form, isn't exactly solving your everyday computing problems. But it did showcase a significant advancement in error correction rates, a crucial hurdle in making quantum computers reliable. What's particularly intriguing, though, is that the Myer One chip takes a completely different architectural approach. It's built upon the bizarre and fascinating properties of the Majorana fermion. Now, buckle up, because we're about to dive into some seriously mind-bending physics. A Majorana fermion is a type of subatomic particle that has the truly peculiar property of being its own antiparticle. Think about a regular electron. It has a negative charge, and its antiparticle is the positron, which has a positive charge. When an electron and a positron meet, they annihilate each other in a burst of energy. What makes the Majorana fermion so utterly strange is that it's like a perfect mirror image of itself. There's no distinct positive or negative side. It's as if the particle and its antiparticle are one and the same. This seemingly esoteric property has a profound implication for quantum computing, resistance to decoherence. Now, this is where things get really, really weird, and where the potential of the Myer One chip truly lies. Quantum computers harness the mind-boggling principles of quantum mechanics, such as superposition and entanglement. Superposition allows a quantum bit, or qubit, to represent not just a 0 or a 1, like a classical bit, but a probability of being both at the same time. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. A qubit exists in a similar probabilistic state. Entanglement, on the other hand, is like having two of these quantum coins linked together in such a way that when one lands on heads, the other instantly lands on tails, regardless of the distance separating them. It's spooky action at a distance, as Einstein famously called it. These quantum properties are what give quantum computers their potential for incredible speed and computational power for certain types of problems that are intractable for even the most powerful classical supercomputers. However, there's a catch, a massive Achilles heel of current quantum technology. Qubits are incredibly delicate. They are exquisitely sensitive to their environment. Even the slightest vibrations, temperature fluctuations, or electromagnetic noise can disrupt their fragile quantum states through a process called quantum decoherence. Essentially, the qubits gradually lose their ability to exist in superposition and entanglement, collapsing back into a regular, classical 0 or 1. Think of it like trying to conduct a choir singing in perfect harmony in the middle of a chaotic war zone. The slightest disturbance can throw everything off. This inherent instability leads to high error rates in current quantum computers, making it incredibly difficult to perform complex and reliable computations. And this, my friends, is where the Majorana fermion steps into the spotlight as a potential savior. Because of its unique, being its own antiparticle nature, the Majorana fermion is theorized to be inherently more resistant to decoherence. It's as if this strange particle exists in a protected quantum state, less susceptible to the disruptive influences of its surrounding. The concept of the Majorana fermion isn't exactly new. It was first theorized way back in 1937 by the brilliant Italian physicist Ettore Majorana, who mysteriously disappeared shortly after proposing it, adding another layer of intrigue to the story. However, actually observing these elusive particles proved to be incredibly challenging. It wasn't until 2020 that researchers finally claimed definitive observation of Majorana fermions in exotic materials, specifically in structures involving islands of gold. Now, Microsoft has a rather checkered history with this particular particle. Back in 2018, they made a bold claim that their researchers had detected Majorana fermions. This generated a lot of excitement in the scientific community. However, that research paper was subsequently retracted when it was found that the results had been misrepresented. It was a significant setback and fueled skepticism about Microsoft's quantum ambition. But now, just a few short years later, Microsoft is back with a vengeance, claiming not only to have observed Majorana fermions, but crucially to have gained the ability to control them. They've released a research paper detailing their approach, which falls under the umbrella of topological quantum computing. This is a fundamentally different approach compared to many other quantum computing efforts that rely on trapped ions or superconducting circuits. Topological quantum computing leverages the unique properties of these Majorana fermions, specifically the concept of Majorana zero modes. These zero modes are localized quantum states that can exist at the ends of a specially engineered nanowire. The magic happens when these Majorana zero modes are physically manipulated through a process of braiding and fusion. Imagine intertwining these nanowires in specific patterns. This braiding operation effectively performs quantum computations. Then, by fusing these zero modes together, researchers can make measurements and extract the results. The entire process takes place on these meticulously crafted nanowires, engineered atom by atom to create the precise conditions needed for Majorana fermions to emerge. At the heart of this technology is a new type of semiconductor they're calling a topo conductor. Essentially, it's a carefully constructed sandwich of a superconductor and a semiconductor, where the semiconductor is engineered to mimic the properties of the superconductor in a specific way. These topo conductor segments, hosting the Majorana zero modes, can then be chained together. theoretically allowing for the creation of highly complex and scalable quantum circuits, potentially reaching those coveted millions of qubits on a single, relatively small chip. Of course, there are still significant hurdles to overcome. The Myer One chip, like most current quantum computing hardware, needs to be kept at temperatures near absolute zero, a fraction of a degree above the coldest possible temperature in the universe. This cryogenic requirement adds significant complexity and cost to operating these machines. Furthermore, while Microsoft boldly claims that their architecture can scale up to millions of qubits, they haven't actually demonstrated this feat yet. The current iteration of the Myer One chip likely contains a much smaller number of functional qubits. As it stands today, companies like Google and IBM appear to be further ahead in the sheer number of functional qubits they've demonstrated and the development of software and algorithms for their existing quantum hardware. However, Microsoft has strategically played the long game here. They are arguably the only major player heavily invested in the topological approach to quantum computing. While others are focused on refining existing qubit technologies, Microsoft has taken a high-risk, high-reward bet on this fundamentally different paradigm. And this is a massive if, with all the historical baggage of Microsoft's past technological hypes, remember the Microsoft kin? Yeah, exactly. If their claims are genuine and their technology proves scalable and reliable, then the Myer One chip could indeed be a world-altering breakthrough. It could be the key that unlocks the true potential of quantum computing, moving it from the realm of theoretical possibility to practical reality. What would that mean for us as programmers and technology enthusiasts? Well, it would likely necessitate a fundamental shift in how we approach software development. We might need to rewrite significant portions, if not entire code bases, to effectively leverage the unique capabilities of quantum hardware. Algorithms that are currently impossible on classical computers could suddenly become feasible. It would be a whole new world of computational possibilities. And speaking of reviewing and optimizing code, I want to take a moment to talk about our sponsor for today's video, CodeRabbit. Now, imagine you're faced with the daunting task of rewriting millions of lines of code for a quantum future. You're going to need all the help you can get in ensuring that new code is clean, efficient, and bug-free. That's where CodeRabbit comes in. It's an AI co-pilot for code reviews that provides instant, intelligent feedback on every pull request. Unlike basic linters that just flag syntax errors, CodeRabbit understands the context of your entire code base. This allows it to catch more subtle issues, like inconsistencies in coding style, potential performance bottlenecks, or even missing test coverage. The best part? CodeRabbit often suggests simple, one-click fixes, saving you valuable time and effort in the review process. And it's not a static tool. CodeRabbit continuously learns from your pull requests over time, becoming more attuned to your team's specific coding standards and best practices. The more you use it, the smarter it gets. CodeRabbit is completely free for open-source projects. And for everyone else, you can get a fantastic 1-month free trial for your team by using the code FIRESHIP with the link below. Trust me, as we potentially enter this era of quantum software, tools like CodeRabbit will be invaluable in navigating the complexities of this new frontier. So there you have it. Microsoft's audacious claim of creating a new state of matter to power their Myer One quantum chip. It's a story filled with scientific intrigue, historical skepticism, and the tantalizing possibility of a technological revolution. Will this be the breakthrough that finally makes quantum computers not suck so much? Only time will tell, but one thing is for sure, the world of computing might be on the verge of a seismic shift. What do you think about Microsoft's announcement? Are you cautiously optimistic, or do you think this is just another case of overblown hype? What are the first real-world problems you'd love to see solved by a truly powerful, scalable quantum computer? Let me know your thoughts in the comments below. I'm genuinely curious to hear your perspectives. Thank you so much for tuning in. I truly appreciate your time as we explore this fascinating and potentially groundbreaking development. Remember to take care of yourself, stay curious, and continue exploring the wonderful world of technology. And if you enjoyed this video and want to stay up to date with the latest tech news and insights, please consider subscribing. Until next time.